Hello, my name is Jolie Hales. I'm with Rescale and I will be the moderator of this webinar. And I wanted to say welcome. Welcome to our fifth of the Rescale Solutions webinar series. And this series features hands-on demonstrations of the top science and engineering applications on Rescale. So we're glad to have you here with us. Today's focus is on how to fast-track design performance mapping with Rescale's Cloud Power Design of Experiments workflow and NUMECA. So I also wanted to let you know, get my next slide going here. Also wanted to let you know that the next webinar in this series will take place 2 weeks from today on Wednesday, July 15th, and that will cover crafting solutions with MSC Cradle CFD on Rescale. So we have these about every 2 weeks or so. And in addition to that, if any of you know any business or technology leaders who may be a little bit hesitant or afraid to move to cloud HPC because of the fears that come with it or the risks that come with it, Rescale, we just rolled out a new interface that gives leaders control, transparency, security, the whole kit and caboodle, so that they can be confident moving forward. And we have a special webinar covering that topic on July 22nd, which will also feature a discussion with, some of you may have heard him speak before, Addison Snell, who is a well-respected HPC analyst from Intersect 360. So you can see clips of the new interface, and you can also find any of our webinar registrations on any of our social channels and also on rescale.com. Okay, so without further ado, let's go ahead and get started. So we have two presenters lined up for today. The first is our featured guest presenter, and I'm so sorry, Alan, my Dutch pronunciation leaves much to be desired. Alan de Millionaire, who is the managing director of NUMECA USA, and he's been that since 2005, where he works on business development and leads a team involved in technical support, software development, and consulting. Alan earned his PhD at the Von Karman Institute in 1997, working on the three-dimensional design of turbo machinery blade rows, where he developed an inverse design 3D solver for turbo machinery blades, aiming at modifying blade shapes in order to meet target pressure distributions. He has worked for NUMECA since 1997 and has become a major contributor to the solver of Fine Turbo and of the blade optimization package Fine Design 3D. Lots of cool accomplishments there. And then our second speaker is Roque Lopez, and he is a technical account manager at Rescale. And he enjoys deep engagement with engineering teams to ensure that the voice of the customer becomes product value. He's a strong believer that we're living in an engineering revolution in the cloud, and he's always in pursuit of his customer success and on a mission to help others harness the full potential of cloud HPC. Roque comes with 20 years experience working with multidisciplinary engineering teams and turbo machinery R&D groups in power, aerospace, automotive, and marine industries that use CFD applications and HPC systems. So lots coming up for us. At this time, I will go ahead and turn webinar control over to our first presenter, Alan from NUMECA.
Okay, what an introduction. Thank you very much. So my name is Alain de Meulenard, yes, working for NUMECA for a long time. It's really my pleasure to be here, part of this webinar. It's actually a first webinar. We intended to do a few together between NUMECA and Rescale. And yeah, I appreciate everybody's time. I understand there are many people, it's lunchtime here for me, but I hear other people may be having dinner while watching this. So we have a large variety of people all around the place. And you know, it's an exciting time for the CFD community with all the opportunities that now cloud is bringing on the table. You know, with most of the the clients have been working with for 15 years using commercial CFD. I mean, NUMECA and others. You know, there's typically a limit to what you can do. You have to work out the budgets. Those budgets are quite often based on an annual basis, so there's a certain amount of things you can afford, and also in terms of computational resources, you have to make decisions, and obviously budget sizes are different between companies, and deciding to purchase 200 cores or a cluster of 2,000 cores is a big investment, not only in money but also in time and staff. And once those decisions are made, it pretty much also determines what you can do with the CFD. And unfortunately, not everybody can afford a 2000 core system. But the good thing about the cloud is that everybody can afford now 2000 cores for a day, or 200 for a few days, and that opens up possibilities, things. And you should not only think about, when you see cloud, I mean, you often see images of huge runs, hundreds of millions of mesh points, and it's not necessarily that. It's also giving you the possibility to run dozens or hundreds of runs at the same time when there's a big load that's needed. So execute, a full performance map evaluation in an hour, or execute a design optimization project, which with your resources could take you weeks and can be done in a couple of days. So this is the game changer. So I know that Roque has prepared some example for us that he will show afterwards based on our software. So now I'd like to spend a few minutes on showing you a few slides about NUMECA, what NUMECA does. So for those who are less familiar with us, we've been around for 20 plus years. Actually created initially in Brussels, Belgium, by the Professor Charles Hirsch, and now we have offices around the world. I'm from Belgium, but now speaking from actually from San Francisco, California. So our office is actually a few blocks away from the main Rescale offices, so easy for us to communicate. And so we have been working all those years on building CFD solutions, so from A to Z. So meshing, solving, post-processing. I won't go into all those boxes here that are on that slide, but we've been developing different type of meshing systems, and some of them actually very dedicated to applications. And it's the same for solvers. We have different solvers. So at NUMECA, we're convinced that it's very, very difficult to build a general purpose solution that will be able to solve anything. So we believe more in dedicated solution. And for instance, for turbo machinery, we've built this package that people know as Fine Turbo. That's for meshing for turbo machinery, solving, post-processing. That's actually on the right side of the slide. That's something important there. This is about design optimization. So that's always something that we consider that's very important and part of your future. And I mean, 10 years ago, it was still quite difficult to do that. And still today, not that many people are doing this intensively. But what's important in there, I mean, obviously to do that, you need optimization algorithms and these types of things. But you also need CFD to work very well. So that may sound a bit simple to say, but what I mean by that, it needs to work smoothly in a robust way. And you need to be able to change your geometry and have the CFD run smoothly without the need for the user to intervene, change the mesh template, find a solution if the solver fails, and things like that. Because if you have to do these types of things, then the process will be very difficult to be successful. So that's something we always kept in mind when developing, and it means also having everything possibly run in full batch from A to Z. So we have been, as I said, we've worked pretty much by market. I mean, turbo machinery is by far the #1 market of NUMECA, but we work also a lot on external aerospace, automotive, marine. So instead of showing you all those names, maybe I'll show you just a couple of examples of success stories and people using us. So here, the first one is Boom. So this is actually a company that works with both Rescale and NUMECA. And so actually, when we started talking to them, they were actually using mainly free solvers available from research. So free solver is obviously very appealing. But if you find a solver, not free this time, a commercial solver, but that can be more than 10 times faster for a given run. So here I'm showing here the test case I'm showing here on the slide is the inlet system. It's quite a complicated system to be designed for this type of aircraft. And you have we have different types of mesh sizes we use for that, but we consistently found out that our approach was about 10 times faster. So if you do the math of, summing up the hardware and the software cost, you can easily determine that actually the free software was not the cheapest option. And so I'll come back to speed, but this is one of the big trademarks of NUMECA, is having worked on solver speed and convergence acceleration. So that's something where we typically stand out. Okay, another example is with Mast and Space Systems, so external aerospace here. So this is a company we partnered with for several years, and we've done different types of things with them. Again, you see here a highly supersonic application. That's also something important for NUMECA, is that actually high speed is totally in our comfort zone, as opposed to some commercial software which are more initially designed for low speed. So here here I wanted to activate this movie. Yeah, there you go, it's launching now. So the type of runs we've been doing, which is quite original here, is that, so for this vehicle here, you want to study a whole trajectory. And along that trajectory, the boundary condition will evolve. So you need to organize that. So this is an expensive run to do. Here it's on government supercomputers that we've been able to do something like that. Other things we've done actually is design optimization. So including some parameterization on that vehicle and being able to optimize that. Okay, and the third one, very different here, is with Honda. So here in automotive, so you see here a complete car that you want to solve. So that's very, it's a big challenge. And when we started talking with them, we were talking about weeks to be spent on generating one single mesh, and then days to be spent on solving. And a lot of things have changed in 10 years. In 10 years, meshing that was almost impossible. Taking so much time. And now we're about, as of today, this is something that is meshed and solved, so both on distributed memory clusters. And the engineering time has moved on from being days and weeks to a few hours. And we have tools, so not only to mesh, but also to prepare this geometry automatically, find the holes, close them. So all that now is available. So we've made really tremendous progress on this type of applications, and that's really helping Honda. So now going more on a few slides about products. And here, this seminar here is based on turbo machinery, so I'll be focusing on that. So from meshing to solving. Now you have seen this slide that I was showing with all these different products, these meshing products, solving. So all that is integrated into an environment. So the name is Omnis, and we're actually very excited at NUMECA. We just released last week the first version that includes all the turbo machinery functionalities. So, this is an environment very comfortable from the user friendliness point of view, where you bring in your CAD, you work on it, you can prepare it, you can mesh, solve, post-process. You actually have, everything is parallel, you can co-process, so meaning that you can look at the solution as you're solving it. And so we would be very excited organizing demos of this if you are interested. So now going into the steps. The first step is meshing, and here I'm putting a very old-fashioned style mesh, if you want to. So mesh, multi-block structured mesh around a compressor passage. And so in order to do that, we've developed for 20 years the tool named AutoGrid. So this is actually the most successful tool of NUMECA as of today. We have thousands of users using it every day. And the big strength is that, you see this topology here that comes out around this cascade. And this topology comes right away to you. So there's no, you don't have as a user to do anything. And what's very important too is that you can use this same topology to successive blade designs, and you can actually change that shape quite significantly, and this template will still apply. So you can close your eyes and mesh this. And this is actually what people do with AutoGrid. They do close their eyes, and by that I mean execute in batch on the design cycle, you can execute meshes like this, and a mesh like this executes in a minute or two, depending on the size. We've actually pushed the limits of what you can do with multi-block structured meshes by including additional things such as ported shrouds, cavities, leakage systems, such as the one you see here, and still have this high quality with multi-block smoothing. So once, that's for turbo machinery passages. When the geometry becomes more general, and there you can think of anything. Then and the same with this Honda car I was using before, there we use unstructured meshes. We have developed hex press for 20 years and developed full hex or hybrid meshes in a parallel way. You see here the example of a volute that's collecting the flow downstream of a compressor wheel, and this also executes in a few minutes, and you can actually then combine. Imagine we are not showing it here on the slide, if you have a wheel that's meshed with autogrid and then an unstructured mesh for the volute, and you can combine those within Omnis and execute the solver. So talking about solver, I will not go about all the details of that, but I was mentioning this speed, and you saw this very big difference in execution time that I was mentioning. There are different reasons for that, multi-grid and other things, but a big one it's a convergence acceleration approach we've developed at NUMECA. We gave it a name, CPU booster. It has nothing to do with hardware, though. It's an algorithmic development, and we have, and you can see here between this blue and the green curve, we have been able to reduce the CPU time very significantly. Of course, it depends on application or operating points, etc. So the speed up is different, but we have achieved computing times that are typically of the order of, so if every core is in charge of 1 million nodes, to give you a reference, typically the full computing time will be of the order of an hour, maybe half, maybe an hour, maybe 2, maybe 3, but that's the order of magnitude. And with most commercial software, you're of the order of 12, so pretty much a work day to execute a run. And so besides converging fast, you also want to take advantage of hardware and being able to scale, not only for the largest runs, but also for the smaller runs. So to take advantage of your cores as quickly as possible. So here you have an example here of a full centrifugal stage. So the wheel followed by a return channel, 500 million mesh size, and we've executed that on different types of size, and actually even up to 20,000 cores, we still have an efficiency that's about 75%. So this is a project that we executed with the Dresser company, now Siemens, actually that was a DOE funded project, so on a DOE supercomputer. And so this is full unsteady using DES type of modeling level, and we progressively decrease the mass flow. And I wanted to show this because Dresser claims that this is probably the first time that numerically one has been able to model the appearance of stall cells. So you see here those pinky zones, we have 3 of them. So numerically we're able to show the appearance of that. So that's pretty cool. Okay, so next, also in terms of acceleration, so you can scale taking advantage of the cores. We have worked on the algorithms. You can also take advantage of the new generation of GPUs. So if you have a relatively recent GPU on your system, you can have all heavy mathematical operations executed on the GPU, and then it takes no time, and you get a speed up. So you see here the type of speed up that you get for totally free, if I can speak like that. So just again, dividing the execution time by a factor of more than 2, which is great to have. Another important, so I was mentioning so meshing, solving time. An important trademark of NUMECA is unsteady turbo machinery. So say the role of commercial software is to bring the results of the research in a professional way to the industry. So that's one of the roles we have. But here, NUMECA can really claim that we have done the research and developed this harmonic solver that is very successful. So the idea here, so in turbo machinery, the unsteadiness, you know that most of the unsteadiness in the signal is included at frequencies we know very well. Those frequencies come from the blade count and rotational speeds. So if you know that, if you decompose this unsteady signal in Fourier series and just take the terms you're interested in, you can actually rewrite another formulation of the Navier-Stokes equations. And instead of solving unsteady over 360 degrees and wait for the convergence for quite some time, as some of you probably know, you can actually, from the practical point of view, using a harmonic option is the same as solving steady state. You're solving equations to convergence. You just have more equations. We have additional equations that are called the frequency equations, where we solve for the amplitudes and phases of the unsteady signal. And so if steady state takes you, say, 5 hours, the harmonic will take you 10 or 15 or 20, depending on how many frequencies you're taking. And it opens up many possibilities. I mean, you have rotor-stator interaction, which you can see here on the top left. So not only you're bringing unsteadiness, but you also have a better modeling of the interactions, because instead of having a brutal mixing plane between the rotors and the stator, you actually have the real flow and the real mixing happening. You can also work on noise, so tonal noise prediction in a very efficient way, fluid structure interaction using the natural deformation frequencies of your blades, distortion and analysis, and etc. So many things you can do with this harmonic. A last slide I wanted to show, I was mentioning design optimization at the beginning of my speech. So this is something that NUMECA does a lot. Our users do it, we do it for our users. And actually the type of approaches we have used, the one we use the most is the one where you need to parameterize your geometry. So we have tools, and especially in turbo machinery, we have developed dedicated tools that allow you changing the blade shape. As you can see here on that movie, I mean, the blade changes quite significantly. And the first thing you do is create a database of run. We call that the DoE step, design of experiments, where you change the geometry, calculate them all, and you get a lot of information. And once this is done, you can proceed with the next step using a surrogate model that will use this database information to find the optimum for you. So this approach has been developed for many years, initially actually at VKI, and then being used at NUMECA to develop the commercial tools. And we have worked also on optimizing other things than blades. You can see here at the bottom of the slide the keel of a hull, so for marine application. And I mean, the cool thing about optimization is it's very general. So your objectives can be many things. So not only an efficiency of a pressure ratio and so the aero performance, but you can take into account other things. So here, this is the compressor of a turbocharger, which is rotating at more than 100,000 RPM. So the management of stress is very challenging. And so if you want to improve the aero performance, it's very difficult to do without explicitly ensuring that the mechanical aspects are okay. So we've done that here on that project. So we included the FEA in the game so that with every geometry we would generate, we could check the stress levels. And here in this project, we did not only improve the choking flow in that stage, but also we were able to decrease the stresses. Yeah, to conclude, another topic that we have worked on the last few years is about uncertainty quantification. So we believe this will be an important part of the future of CFD. So, you know, as of today, when you execute CFD, you assume that the geometry is very well known, the operating conditions are known, but in reality, you have uncertainties on everything. And it's important to take that into account. And this is what UQ does. So first of all, quantify the impact of uncertainties on your results. That's the first thing. But the other way, if you see it in the design way, you can also do a design, and also if you know you have some uncertainties on something, say on the geometry, on the tip clearance, you can also ask the optimizer to minimize the sensitivity to those uncertainties. This is what you call robust design. And sorry, I'm jumping here to the last slide. So here we re-executed this design exercise and taking into account uncertainties. And you see we come up with a different design. So which was a little bit less exciting from the performance point of view, but which was more robust. Okay, I gave you in a few minutes, I showed you a lot of different things. Feel free to ask questions. I'll be happy to answer them probably at the end of the session. But at this time, yes, it's time for me to give the stage to Roque to show us some examples.
Awesome. Thank you so much, Alan. I appreciate that interesting stuff. And as he said, if you do have any questions about NUMECA and anything he's presented here, feel free to write those in the question window. We will get to them. And at this time, I'm going to change the controls over to Roque. Roque, do you have the power? Go, go, gadget microphone. There you are.
Thank you for that, Inspector Gadget reference, Jolly.
I'm aging
Hello,
myself.
everyone. Alan, thanks a lot for that wonderful review of NUMECA. And it's pretty clear that the NUMECA tools are awesome. They can scale pretty well. And well, a lot of these workflows that you presented indeed demand running a lot of simulations. And today I'm going to focus on well, showing a little bit of that, a quick example that would be representative of what you would normally need to do in order to obtain, for example, a performance map of a design. So let's get to it. Well, let me start with a simple notion, or rather a question. So, what is the most precious resource in innovation? I personally believe it is time. Time is definitely the most precious resource that any person, engineer, or even in the industry that we all have. And the sad news is that it's a very, very limited resource. So true, time is money, as we all know, and well, specifically in the engineering, design, and simulation world, we want the engineers and scientists to better spend their time rather than investing their time in understanding and processing their designs data, rather than waiting for that data to be generated, right? So we love being there, waiting in a queue and bored to death until we finally get our results. So from an industry perspective, a very high level. So let's see a very familiar timeline. So a typical time to market timeline without HPC would probably have a very, very long and costly prototyping and physical testing phase, the so-called design trial and error iterations. And yeah, eventually you will have your design, but most likely your competitors are going to beat you. However, with HPC, the game changes quite a bit, and we have been living this over the last decade, and in the most recent years, it has even boosted even more thanks to the HPC availability in the cloud. But fundamentally, this is how your time to market timeline is affected. So you will reduce your prototyping physical test, because you will be able to create virtual twins of your concept designs, of your design concepts, and then iterate on them in a virtual safe environment that is also pretty cheap when it's compared to actual physical world testing. So that way, when you get to the prototyping, you're ready to go with a clear and most likely to succeed idea, and well, you will be able then to manufacture and deliver way faster. And this is not just time savings. This will also represent a money savings, but most importantly, that you will be able to be ready to sell your product to the market faster than anyone else. Now, if we could look inside our engineering minds, I'm sure we have a lot of stuff to worry about, especially in these strange times. But when we focus on our engineering and design simulation work, we probably will see these bigger bubbles here. So you have your engineers. We are always worrying about the numerics and the modeling of the virtual twins of our concept designs, and we're trying to spend as much time as we want, as we can, understanding performance and trying to find those little opportunities that will make our design better. But also, especially when dealing with the simulation that is required to execute design iterations with these virtual twins, we will often hit a bottleneck, especially when you're working with limited compute resources. Whether you have just a small little laptop to work with, maybe you're a small consulting firm and have a couple of workstations, or whether you're a large enterprise where you have a large HPC cluster or a medium or large HPC cluster. Either way, in that scenario, the fact is that those HPC resources are limited. So for example, if you think of a single engineer, they will have probably some jobs to run, and whatever limited HPC they have, it's also shared with all their peers in their company. So you spend a lot of time in queue. So for example, here we're seeing a few jobs and they're just waiting in the queue one after the other. Why? Because my on-premise HPC is limited. That, in addition to the fact that to get there to have that on-prem HPC system, there was probably a lot of investment behind it, and there is a lot of capital expending to get there, to maintain it, people to service the cluster, installing schedulers, solvers, and so on. So it's more than we just oversimplify with this little diagram. But now, what happens when you move to the cloud? Well, first of all, you forget about that problem of having to build and maintain your cluster. So it's just there. All the resources you want, they're just there, and they're virtually unlimited. So you could essentially, if your jobs are independent from each other, you can just launch them simultaneously and have a huge time savings because there is no queue and your jobs are going to produce results a lot faster. But in addition to that, we at Rescale excel at offering you not just access to the HPC cloud resources, but also access to optimized environments where the applications and the resources and the different architectures are already married to each other in such a way that you will be able, for example, if you need to run CFD, you will have access to the best core types for CFD, and we will give you recommendations on that, and we will help you build your solution on that. Same thing for FEA, crash analysis, electromagnetics, you name it. So what happens here is that you effectively have, with HPC in the cloud, immediate flexibility, scalability. You will get faster results and obviously a shorter turnaround time. So now, how is that presented to you from a user perspective? So this is the Rescale. We built for you the Rescale platform experience. So we have packaging. We have packaged everything you need in our customer-centric platform. Let's take a look at the ingredients. So we have on one hand, in the back end, the fully integrated stack of enterprise deployment tools. So everything you need to be able to have the platform and the service live and ready to go for when you need it. And then you have also, we also have the ingredient of being one of the most compliant and secure platform. So we offer total security control and compliance. So we have certifications for security, SOC, ITAR, HPAA, HIPAA. We're working on obtaining our FedRAMP moderate certification. It's all there. We're just waiting for things to move along with receiving the certification in this time, pretty soon. In addition to those comprehensive administrative controls and the ability for the IT managers and decision makers of the companies to build and implement security policies with us very easily. With respect to the user's data, we guarantee whether you're working under one of these certifications or not, we guarantee in-transit and at-rest encryption of all your data. So everything you do is super safe in the cloud. And well, in addition to that, we have access to the most comprehensive cloud ecosystem. So you can truly accelerate innovation. You can pivot instantaneously from the same job definition. You could easily pivot from one cloud provider to another, just to be able to access the best technology that maybe for one application, it's better to work with a certain core type for one cloud provider, and for another one, you will work with another core type from another cloud provider. So you can easily pivot like that with almost with virtually no limitation. And then, well, you also have access to the optimized environments and installations of your preferred software applications. So today we have our little demo with Fine Turbo from NUMECA, but briefly, I will just say that not only the turbomachinery industry could benefit from such a powerful and fast tool as NUMECA. We have also aerospace, multi-physics, marine, on optimization. By the way, what we're seeing today is not necessarily a optimization, but we will have definitely a dedicated optimization webinar where things are more exciting. But what we're going today is pretty much the foundation of what it's going to take you to get an optimization environment on your enterprise. Then let's see here. So performance mapping. Oh yeah. So today's example, actually, what I'm going to show you, it's a performance map. So as you probably know, if you're familiar with building this type of performance maps, they're very typical. These ones from a compressor, a centrifugal compressor. So you will see that you have to explore your compressor design range from a variation of speed lines. That's RPM at which the impeller is going to be rotating. But then from that RPM, you also have a range of different flow rates at which the compressor is going to be processing the work fluid, and this will deliver different performances in terms of pressure ratio and efficiency, for example. So this type of speed line is the result of exploring that operational range of a single design. Each speed line, as I mentioned, corresponds to a variation of RPM, flow rate, back pressure, etc. And each red curve there is plotted by running several CFD computations. So each red dot that you see there on screen is actually one CFD simulation. And you want to obtain as outputs performance and pressure ratio and so on. So that's the type of model that we're going to explore today. So how are we going to leverage this in the cloud to speed things up? So we're going to tap into the Rescale platform, and instead of using a simple batch job and launch one simulation at a time, we're actually going to tap into the power of the design of experiments workflow that will allow you to parallelize all the simulations and extract all the data of your model. In this, it doesn't matter how many simulations you have. In this case, my model has about 15. They will take the same amount of time it takes to run a single job. So as inputs, you bring in the virtual twin of your design in shape of a mesh for CFD in this case. Then you set up the parallel settings. This is how the different variables of the operational range are changing: RPM variations, flow rate variations, back pressure variations, and so on. And then the system will build for you all the different jobs that you would need to run to complete that matrix of parameters. You will have the opportunity to select a few post-processing instructions, as well as selecting the best core types from the cloud for your simulation, and then you will obtain all your results for data mining or processing in the ROM. So let's take a look at this live, actually. So let me switch here. There. So when you, this is where we're going to get at. So this is how my DOE simulation went. I launched 15 simulations simultaneously, and with the super fast conversions of NUMECA, each of these simulations took 17 minutes to complete. But because I ran them parallel, they all run together at the same time. And then from there, you get automatically your matrix of results. So here you obtain a quick table of results and simulation. You can download this to process, for example, in a spreadsheet very quickly. So you can automate all those post-processing workflows of the important data. Moreover, you can also jump into the post-processing tool that exists in the cloud and perhaps start creating a few plots there to take a look at the performance response of your simulation. So you can do that there, and let me show you now how you get there. So first you start logging into the Rescale platform, and you will have your welcome page. For those of you that are new to the platform and you would like to learn about a basic batch job, I invite you to take a look at one of our previous webinars. We have fantastic webinars that review this in detail. But suffice it to say that you're here, you have access to the documentation, you have access to a series of tutorials, so you can really quick in a matter of half an hour how to use the Rescale platform. And then we're going to show you now how to submit a job. So to submit a job, you click on the Create New Job button on the bar. Let's say that I want to give this job a decent name. So DOE Fine Turbo HPCC. That's the compressor I'm running on today. And I'm going to switch my job type from basic to design of experiments. We also have frameworks for optimizations, and we also have frameworks for end-to-end desktops that will be discussed on separate webinars. But for now, let me switch to DOE. Yep, I want to switch to DOE. And you can see now that the workflow has changed a little bit. You can easily navigate through the different configuration pages of the workflow. So let's do that. I'm going to bring in my input file, which is just my mesh from, I already have it in cloud storage. You can upload, of course, from your computer, or you can set up and attach a storage device if you prefer. Then let's go to the next step, which is the parallel settings. Here you can type in directly the values of the parameters that you want to vary. But most likely, if you're a power user and you're working with a very large data set, you might have already a spreadsheet of data that you need to process. So you can bring that data in the CSV format quite easily. So I'm gonna add that there. And let me see, I'm not missing anything here. No, that's perfect. Yep, and once you load the text files also in the platform, you can review the contents of those text files and even edit them. Let's say that for some reason you're iterating and you decided to change some pressure level or boundary condition quickly. Instead of starting all over, you can simply come back to your job setup, change things here, and that will be saved directly and processed directly in the cloud. Then in the next step, you do the template definition. So the template definition is actually that you bring the file that contains the simulation settings. And sometimes you need a companion file. In this case, it's a simple Python script actually written with the NUMECA API for Python that will allow me to say, to interconnect, okay, so the table I have to solve from my parallel settings in the project file using this template, please update the boundary conditions as needed. And same here, you can view that script there directly. You can see all the variables that we're changing, rotation speed, pressure, mass flow, and so on. And if you need to change that on the fly, you could do it as well on the cloud. Then in the next step, we select the software to run our simulation. So today I'm going to work with Fine Turbo. We have a library of nearly 400 different applications available for you on the cloud, and so that's something that you would see if you log in directly into the platform with your own account. Now for Fine Turbo, well, you choose the version. We have tutorials in the documentation as well. So if you need quick refresher on how to set up your files, your input files, and your mesh for this type of simulation, you can check out that tutorial there. And then in the command line, here you have a basic template of how the software is supposed to run in the cloud. But in this case, I'm going to actually introduce a little bit of a different command line, because I need to execute the command that tells FineTurbo to update the parallel settings from the template. And then I need to execute each simulation. So each job will clone this instruction to run the simulation as well. Then I have to use to choose the license for the software. So with NUMECA, we have on-demand license available in the cloud, but you can also bring your own license if you want it. So I'm gonna check on-demand license, and now I'm gonna get to the exciting part, which is to build the cluster, to build the computers that that will solve my model. So I know that from the parallel settings I have 15 templates to work with. So I'm gonna allocate 15 slots. That's effectively 15 simultaneous jobs, and I'm gonna tell how many cores I want for each one of these jobs. So actually, you can grab from cores, or you can select cores, or you can select directly nodes. So I'm gonna select a complete node for each job. The default recommended core type in this case is Onyx, quite accessible core type, very performant for CFD. And I get here a summary of the hardware that will be allocated for each slot or for each job, if you want to look at it that way. And also I will set my wall time. This computation will run for less than 20 minutes, but I mean, you can set your wall time as a security measure, so you avoid your job from running for a long time. And then here you have also the list of core types that are compatible with the software, and you can see here a summary of the architecture, memory, the CPU type, the interconnect speed, the amount of storage that each core type has. So all these, so you have a wide variety of core types that are available in the cloud ecosystem. And then I can click next. And in this step, post-processing, this will allow me to link a post-processing script. Same idea, you can view or edit the script there. And I'm going to also bring in here the post-processing command. So this is the instruction that will help you extract the data that you need for your analysis. And that's it. You get a job summary, and we submit. Now, when the job starts to run, you will go to the status page, where you will see the different phases of the lifetime of your job in the cloud. We validate your inputs. We check all the preconditions that are needed for the job to start in the cloud. Then we start spinning up the clusters, and then eventually you will see that the job status looks something like this. This is something I launched before the webinar, so it's already running. And for a DOE job, you will, when you reach the running job phase, you will actually have the option to live tail any of the 15 simultaneous computations right there on the fly. So you can see the output of the processing of the computations. You can also track the progress of the solver. You could also access via SSH to each one of these compute nodes in case you need to take a peek directly with a more custom command line any of these computations. So for example, here I can just quickly jump into one of these compute nodes. I can check how the cluster utilization is going on. I can see all my solver, FineTurbo solver instances right there live. And then I can, there we go. For example, I can go to the work directory, and I can see there the complete set of solution files being produced by the NUMECA solver. You have also a job log history, so this will tell you all the metadata of the lifetime of your job on the cloud, how the platform has been preparing, managing, and administering, and supplying you with and running the workflows from the cloud. And then eventually, once the job is done, you will see something like this, where the job naturally ends, all the computations finalized. You have your complete summary of the lifetime of the workflow. But more importantly, you get also now your summary of results directly. So this is a CSV file that you can download and then start post-processing on your spreadsheets and data analysis tools. But as well, you can access each one of these simulation runs and take a look at the local results for that simulation, and then work with the local simulation files that have been produced by each one of these jobs. So, so from here, just to finalize and conclude my demo, sometimes you not only need to look at the global performance data, sometimes you might need to actually do some pre and post processing in the cloud. So with Rescale, we offer that as well. We have the ability to help you create your own custom desktops. You can easily select different virtual desktop configurations. You can select the software that you want to run in the cloud. So right now we have installations of Find-Turbo and Omnis available for you to use. You can bring in same thing, license and so on. And eventually, once you start and spin up the desktop, it will be living there on your Rescale platform interface. You can access that. You can see the health of your desktop and connect. And if you need, for example, to add more files or change the settings a little bit, for example, let's say that I want to add another job to my desktop and so on, you can do that. You can mount those jobs at any time. And I have already loaded my desktop here with a quick demo. So this is my desktop of today that I used to prepare the DOE workflow. That's the Find-Turbo interface. I loaded one of the solutions so we can quickly see convergence histories and so on. Let's say that for some reason I wanted to change one of these computations and maybe launch it in the cloud. In fact, you can. So these desktops are completely integrated with our platform. You don't need to re-log in on everything. It's all natural. So you would just select your job files, go through the desktop to the platform, and your job would be ready to launch. And then you have here, let me show you just quickly a post-processing tool. So NUMECA's CFView tool, it's quite interesting in the sense that it's very easy to automate workflows and do some very cool post-processing, all with a series of Python scripts. And you can work with those scripts in batch mode or interactively. And like I'm showing today, so for example, here we have our centrifugal compressor assembly with some streamlines of relative velocity. But let me quickly just to finalize, give you a quick peek on how the virtual desktop experience is. So you can easily manipulate and rotate the design in the cloud. You can turn on repetitions and so on. And right now I'm just going to execute a quick script, for example, to do a very easy, simple, straightforward static pressure post-processing of that compressor. And there it is. So as you can see, it's pretty much as if I was working on my local workstation, and that's the type of experience that you will gain with Rescale. So that concludes my demo. I'm open to questions. I give back the floor to you, Yoli.
Great, thank you so much, Roque. Appreciate that. It looks like we do have a few questions here. We're getting close to the end of the hour, so if we go a couple minutes over, you're welcome to hang with us for a little bit longer. So the first question is, can you bring your own licenses, and how reliable is it to keep the job connected to my license server? And that's from Josh.
All right. Well, Josh, thank you for that question. Yes, so definitely, you can absolutely bring your own license. So you can use, of course, the on-demand licenses from the cloud, which are great for burst demand or big projects that may come up to you. But you can definitely bring your own license. So what we do is that there are different levels. So we can establish a simple IP forwarding or an SSH tunnel via license proxy. And we can even step it up by implementing a robust and secure VPN connection to your on-prem server. So that's definitely doable and part of the services we offer.
Great, there's another one. It looks like this one might be for Alan. This is from Bernardo. What do you gain with unsteady, and how much extra time does it take?
Yeah, so I was mentioning unsteady in there. So yeah, when you do turbo machinery, I mean, most of the runs, and more than 90% of the runs we all do every day, are steady state. But when you do that, you need to apply a model between rotors and stator to average the flow. We call mixing plane. So we know we're losing something. So by bringing unsteadiness, you get closer to reality. So that's the advantage. Now, unsteady in a traditional way means meshing everything. By everything, I mean 360 degrees and solving time. And typically you need several rotations. It may be 3, it may be 5, it may be 10. So you may be looking at a run that's 2 orders or even 3 orders of magnitude slower than steady state. So there's a big price to pay. So what I was showing in those slides on the harmonic before is that, so with this harmonic solver we've developed, we're only focusing on blade passing frequencies. And so we're losing other things, which are normally of lesser importance. And you can just solve in 2, 3, 4 times the time, which is not that much. It's more time, but it's affordable, and it gives you a solutions that physically closer to reality.
Great, thank you. This one is for Roque. This is from Krista. Regarding ITAR, how do you ensure only US persons work on the platform?
Oh, that's a great question. So thanks for that question. So first of all, I think we have some dedicated materials for you to share, of course, with more details. But to give you the high-level overview of how ITAR works first, it is a dedicated platform. So users that work on ITAR, they would not log in to the regular Rescale platform. They will have an ITAR dedicated platform just for them. And now the registration process is a little bit different because it requires the applicant to submit proof of being a US person or citizenship. And this document is then vetted by our security team and the enterprise security team where they work. And so that will get you access there. Now, in addition to that, well, we have the encryption at rest in transit. We give you access directly to only GovCloud environments. And well, you can also implement security policies in coordination with the security team of your enterprise to set up VPN, IP authorization lists, and login, multi-factor authentication, single sign login, and things like that. So we can offer that. That's how we would offer you the ITAR solution.
And let's see, it looks like we just have one more, unless I get any more questions. This one is from Abdul. I understand how you scale large jobs and how important that is, but for smaller jobs, what do you actually gain by scaling? I think that might be for Alan.
Yes, thank you for that. Yeah, I think I understand. So, obviously, when you have large jobs, there's actually no node that can do that. You need to scale. When you have smaller jobs, so I understand the question. You could say, well, I could actually execute all those jobs serial because that's where you get the best speed. But in reality, and typically in clusters, you would use at least a node which already has a certain amount of cores. And you could question if those jobs are small, if it's worth scaling. But we've been working on parallel scalability, and what's important to look at is the number of mesh points that every core is in charge of. Now, the limit has become lower and lower. And as of today, even if you have a load that is as small as, say, 30,000 nodes, you still perform pretty well, which is good news. So meaning that even if you have, say, a 200,000 mesh, you can still scale and use a node, and the scalability one node then, and the scalability will still be okay.
Okay, great. It looks like, oh, we do have another one coming up here from Kiran. If I say your name wrong, I apologize. What is the upper limit for the parallel job execution based on license, cost, and storage? 100, 200, or customizable? Thank you.
Well, if I may answer on the HPC end of things, yeah. So whether you're working on demand or on demand pro, we didn't have time to look into that, but there are we can customize definitely the maximum limits to your needs. Most of the time, actually, these maximum limits are imposed by your IT administration or management on your enterprise. But I mean, they can be quite large. It's pretty much what you need. As far as the software goes, I mean, Alan, I let you answer in terms of the licensing options for NUMECA for high-end HPC.
Yeah, I mean, here the limit, and you know, if you work with a license that's provided, I mean, when you either you go to the cloud, and we come back to the question that was asked before, and you can use, I mean, there are licenses available at Rescale. So without any agreement with NUMECA, you can go to Rescale and execute a run. Now, if you're using your own license, that is an agreement then between NUMECA and you, then there is typically a number of cores that is allowed, which is part of, I mean, the price agreement that's set. And this maximum number of cores can be 4, can be 8, but can be also unlimited. So that's part of the agreement.
Excellent.
Great. Okay, Roque and Alan, it looks like that was our last question. Thank you so much, both of you, for presenting, and thank you all who joined us for this webinar today. Just another quick reminder that the next webinar in this series will take place on Wednesday, July 15th, with a special webinar for business leaders on July 22nd. So again, thank you for joining us, and if you're here in the US, have a safe holiday weekend.
Thank you very much.
Thank you.